21 and 22. Welcome back. Anyone who's not here, that's like Justin, I don't know where that guy is. And people watching at home. Woo. It is recording, I believe, yeah.
Don't forget to like, comment, and subscribe.
Right!
You're actually going to have to finally do some editing. Take that out.
No, never done any. One time I edited, like 5 years ago. I got really mad at it and like screamed at them so much. I need to take that out. Good. 21 and 22 was the homework. Woo! Let's do it. 21 said something like, prove given two lines that there is a point that is on neither of them. Yeah? Okay, so theorem, given two lines, there's a point on neither of them.
What?
Alright, so, what are you losing?
My brain.
Whoa. Sorry.
Almost gone.
Good. So wait, like I was saying, let's go. Notice how I said in the directions for this homework, don't use the theorem that we proved last class, because if you're allowed to use that there's like such and such number of like points out there and such number of lines, then it kind of becomes like a little like trivial. So this was sort of an exercise. How did it go? Gossett had a proof in the back of the book that was pretty decent. Let's do just one of these two, 21 or 22. Which one do you want to do?
22.
You want to do 22? 22 is the exact dual of 21. So in theory, if you could do 21 and you have achieved the transcendence of duality as I have, then you should also be able to do 22. But I don't know about that. Somewhere there's a good marker. I lost it. No, but there's only so many good markers. Alright, it's a riveting video so far. Good. Let's do 22. 22 is the dual of 21. It says, theorem, good. Theorem, given 2 points, given 2 points, and let's just call those points P1 and P2. There is a line through neither of them. What are you doing? Just throw the marker and get it over with. Good.
Marker.
Guys. Let's focus.
Let's go. Okay, so first there's this point P1, and there's this point P2. And immediately, here's what I know about these points. They are, in fact, distinct. And so, by FPP1, we have a line L through both of them. Cool? Say cool. Okay, so this is L. Great. Well, what now? I need to show there's some other line that doesn't go through P1 or P2. And here, what we are now going to do is we're going to invoke FPP3 prime. Yeah. By FPP3 prime, we have 4 core lines, no 3 of which concur. Those 3 of which meet at a point. All right. So, perhaps I should have begun this proof at the beginning by saying that this is a proof by contradiction. So, I forgot to write that. So, I'm just going to squeeze it up here. Suppose that all lines go through P1 or P2? Who is with me? That is what we need to show is false. So on the supposition that all lines go through P1 and P2, which we shall show leads to a contradiction, then where are our 4 core lines? Well, we got 4 of these lines, man. Every line has to go through P1 or P2. So let's consider the possibilities. Could all 4 of the core 4 lines go through P1? Certainly not, because no 3 of the core 4 lines can meet at a point. Could 3 of the lines go through P1? Also no, because no 3 of the core 4 lines by FP3' can meet at a point. And so in fact, the only possibility, if no 3 of them can meet at P1 and no 3 of them can meet at P2, is that 2 of them meet at P1 and 2 of them meet at P2. Okay? And in fact, L cannot be one of the core 4. Because if L were one of the core 4, then where would the other 3 lines of the core 4 go? Well, if you tried to put all 3 of them through P1, you'd have all 4 lines meeting at P1. That's a no-no. If you tried to do it in a 2-1 breakdown, which is the only other option, right? Well then, you'd have 2 of the other core 4 going through P1. Well, that would already be a contradiction. Who is with me? I don't feel like writing all of that down, but basically, and there's probably like a very elegant way to say this with some pigeonhole or something, but basically, if we have 4 core lines, no 3 which concur, but every line must go through P1 and P2, the only way for this to be possible, by all the cases that we just talked out, is that 2 of them go through, I'll just write, so 2 of them go through P1, and 2 of them go through P2. And I will sort of say in parentheses, and L is not one of the core 4. Because that leads to a contradiction with once you account for the other 3 lines. Who's with me? Now I'll bust out the W log and I'll say, without loss of generality, let L1 and L3 go through P1, and L2 and L4 go through P2. Okay, so now I'm going to draw these in. This is actually very similar to our show that every line has 3 points on it. So there's a certain configuration, kind of like a rose. Okay, so what do I have? I have P1 is on L1, P1 is on L3, and I have P2 is on L2, and P2 is on L4. Okay, and someone make sure the camera's like being rotated properly. Right, well, now a little bit of, oh, and I also know that L is not L1, L is not L2, L is not L3, and L is not L4 by the previous discussion. Okay, well now, why is this a contradiction? That like point of intersection, right? In particular, all these lines meet, man. L1 and L2. Oh, I guess I should maybe even say more things. Like, this is kind of annoying, right? But like, P2 is not on L1, for example. Do I know that? Yeah, I do. P2 is not on L1. Why?
Just take the campus.
Was on L1, P1 and L1, P2 and L1, we know.
Ah, yeah, P2, I'll just say, if P2 is on L1, this is going to take forever, I'm starting to realize. If P2 is on L1, then, can I just write, then L equals L1? right? Because now these two distinct points, P1 and P2, there is already a line through P1 and P2, it's L. But if L1, which already goes through P1, were also to go through P2, then L and L1 would both go through P1 and P2, so then L would equal L1. Well, that's a contradiction. So P2 is not on L1. Similarly, all the other three things that look true are like true, right? That P2 is also not on L3 by the exact similar argument, and that P1 is not on L2, and P1 is not on L4. Who's with me? Okay, good. And therefore, these lines which appear distinct, in fact, are. I guess I already had that all these lines were distinct from each other. That is FPP3 prime, so I don't need to waste time with that. So let's call L1 intersect L2. Let's give this point a name. Let's call it like X. And L3 intersect L4. Let's give it a name. Let's call it Y. Okay. And I know that that those every two lines meet. They are distinct lines. They are part of the core 4. And L3 intersect L4 also meet at this point Y. Okay. And now I can also say, of course, that so why is X not on L3, say?
It's on L1. And P1 is also on L3 and L1.
Yeah, that's right. If X were on L3, that's bad. Because if X is on L3, that means that both P1 and X are on L1 and L3. And that can't happen. What's the giggling happening for? So that's a contradiction with the fact that we have these two distinct points meeting in two distinct lines. And I guess I know that X is not, there's so much work to do. I don't really want to do it. I know that X is also not P1 because, why not? Because it's on L2 and P1 isn't. Right? So P1 is not on L2, but X is on L2. So X is not P1. And similarly, X is not P2, Y is not P1, Y is not P2, for reasons that, like, if you do it out, you'll see. Right? Just like this. Repeat 3 more times in different arrangements. Okay, similarly, so this is a contradiction because this would have two different points, P1 and X, with two different lines through those points. Okay, so I have that X is not P1, no, what was the conclusion of this? X is not on L3. And fine, and then 3 more claims, right? That X is not on L4, similarly, and Y is not on L1, and Y is not on L2. I'm not even positive that all of this is really necessary. What do I finally kind of want to do? Have I shown that X and Y are not equal to each other? I probably have, right? Because X is on L1, say, and Y isn't. So also X is not Y. All right, now finally I'm gonna make a line. Woo! And let's, with color, I will make this line M in red so people at home can see clearly that we now have a line by FPP something 2, 1. Since X is not Y, we have a line M through X and Y. So X is on M and Y is on M. And this, I claim, is the line that doesn't go through P1 or P2. First, some quick bookkeeping. Note that we have to go through this business again where we're like, yo, y is on M, but what's not on, y is not on L1, say, right? And so M is not L1. And similarly, M is not any of the other ones either, man. M is not L2, M is not L3, and M is not L4. Are we okay with this? I feel like we're sophisticated enough now that we can skip the details. Once you see one, you just repeat 3 more times. Woo! Exercise for you, and the reader, and the watcher. Why does M definitely not go through P1 or P2? Well, if P1 were on M, say, what's wrong with that?
L1, L3,
Wait, what? So wait, if M, P1 was on M, then you would have you'd have M being L3, right? I think is the problem. Or L? No.
Or L1.
Or L1. Sure, yeah. Both are problematic, right? So I'll do the L1 way. So if P1 is on M, then here's what we have. We have X is certainly on M, but also if P1 were on M, then we have a problem because in fact X and P1 sort of define L1, and then we would have P1 P1 on L1 and X on L1, and the conclusion of this would be that L1 equaled M, but it doesn't, as we showed. So this shows that P1 is not on M, and similarly P2 is not on M, and therefore we have constructed a line M that doesn't go through P1 or P2. So, all right, how are we doing? Do you guys do something like that? Maybe skipping many details, but the picture was the same? Good. This is the exact dual logic, I hope so, of the logic that Gossett used in the back of the book. If you read his proof, it was pretty good. He used an annoying notation, I thought, but the picture was clear. All right, good. We are done proving theorems about the finite projective plane, sort of. Someone asked off camera, what is the whole point of this anyway? And I don't really have an answer, like a good one, but suppose that, suppose that you were convinced that Latin squares are very important. After all, they assist in experiment design. Well, you're in luck because Latin squares and finite projective planes are kind of just the same thing. And what I shall now present, without further ado, are algorithms to convert any Latin square into, well, specifically to convert, which one are we doing first? This doesn't matter. I shall convert a set of mutually orthogonal n by n Latin squares into a finite projective plane of order n. Are you ready? No. All right, and I would like to say that I've been teaching this class for I don't even know how many years, 7 years or something. Every time I get to this section, I just throw my hands up in desperation and just give up. I just mumble some crap and show them how to do it, and then when it comes for them to explain why, I say like, look man, I have no idea. I think one year I attempted it, some kind of hand-waving argument, and I let the class take over and we got somewhere. But then, there's this guy named Stav. You know him?
He was just here.
He was just here. He came up to me after class last year and said, dude, there's like another way to do this better. And I said, you're right. And then I forgot everything that he told me. Actually, what normally happens every year is I like spend hours and hours and hours teaching this and teaching this and teaching this and helping students try to understand the algorithm. And by the time I'm done talking about it for hours, I kind of realize, oh yeah, this is actually quite simple. Gossett, if you're listening, you did a terrible job in this section. And it's very, very unclear. So I'm about to give a lesson for the first time ever, hopefully, well. This topic, I should say. This topic, well. And it is due to basically stuff. So here we go. Let us, but I didn't write the first part down.
Are we just the best grade? Is that what it is? I think we are just the best grade.
We're just behind the best grade. That's what
You
makes it
are
good.
one of the best grades, yeah. Good. All right, here we go. How the hell is this damn thing? Here it is.
Yeah.
Yeah, you have to like.
Woo! Okay, take the following two. Good. Take the following two Latin squares. 1, 2, 3. 2, 3, 1, and 3, 1, 2. And 1, 3, 2, 2, 1, 3, and 3, 2, 1. Okay, so note that these are both Latin squares. Definition of Latin square, each number 1 through 3 appears exactly once in each row in each column, so just duh. These two Latin squares, I claim, are also orthogonal, mutually orthogonal. And that is because, what does that mean? That there are no ordered pair repeats itself, right? So this is 1, 1, 2, 3, 3, 2, and you can just see that is going to be the case for these two. Okay. Good. Now I shall convert these two pairs of. I shall convert these two Latin squares into a finite projective plane model of order n. Whoa. Okay. How do we do this? The stop method goes like this. The stop method is 0 lines. The entire algorithm is you're just done already. Because already,
Whoa.
that's the kind of thing he would say if he were there. He'd be like, but see, these are lines, right? Take those line of 3s, that's like a line. And the line of 1s is like a line. And the line of 2s is like a line. And this line of 3s is like a line, and a line, and a line. And then you have the horizontal and vertical ones, and that's it. So, so that gives you the affine points, and you just add your points at infinity and you're done. Woo! So, and this is the level of detail he provided to me in his explanation over GChat. So, anything over and above that is my work. So here we go. Let's take the 9 affine points of the 9-point model. Am I doing this right? Yes, I am. Of course I am. Yeah. Okay. And now let's just sort of maybe we give these points names. So let's call this point 1, 2, 3, 4, 5, 6, 7, 8, 9. No, that's fine. Yeah, maybe not the group.
This one's burning.
Do we have enough color to do this properly? Where's that marker you guys were throwing around?
This one's very. This one's cute.
It's regular red. I need 3 shades of
I'm so confused.
blue. Alright, wait, stay with me now. Staying together. Class. Okay, good. So, good. Here is one equivalence class of parallel lines. There is the line through the 3s. Then there is the line through the 2s. Then there is, oh, what have I just done? Alright, I forgot to switch colors.
I don't have color.
It's very dirty. Were you the one, was that last year that you refused to
Erase the-
erase the board because it got your hands dirty? Wait, which color should I just use?
Hey,
Are you sure?
yeah.
You're positive. You saw me put that down? Okay. I don't know if you're right. I think you're wrong.
Very long.
What?
Actually unclear. These colors are not
It's the
distinct
same.
enough, even in person when I'm standing right here.
No.
Never mind!
Like the same.
Dude, there's like
Very
art.
similar.
The same
Color
color.
I don't know if it's
Shut up.
I mean, it might be.
You guys didn't hear
They're
that.
just like way too similar to be useful. Alright, whatever. Wait, staying focused. Those are, do you agree that those are 3 parallel lines? Okay, why do I know that they are going to be parallel? Can we get a little bit more of an analytic proof here? Please invoke properties of the Latin square.
If they intersected, the one number would be 2 numbers, right? And if they can't, yeah, problem.
Wait, isn't it? Because this was my objection to stop, which I didn't get to have because we didn't get to have our conversation. It's not really a proof to just be like, I drew a picture, I'm done. Like I need to hear a little bit more, like some words and stuff, right? I know, I think you're on the right track. You're laughing for some weird reason, but right? But like, why do I know that this is going to happen? In fact,
It's like 1 in each row.
I guess like literally, there are the 9 positions in the square are the 9 points, and so like, there's only freaking 1 number in a box. So these are just 3 have to be parallel. Is it that simple? I think it's that simple. Yes. I think it's that simple. Do you agree? Okay, good. Yeah, they can't meet at a point because that would be the equivalent of having 2 numbers in the same freaking spot of the square. Okay, that did deserve some laughing. I agree. Okay, now I shall add. Wait, this is getting intense. I now shall add the next equivalence class of parallel lines. These ones. Woo! So here we go. Cha cha cha. Zoom. That's the 1s, then we got the 2s, and the 3s.
Where is the thing?
That was my attempt at spooky noises. Alright, and now, of course, they will meet off. They will all meet off at a point at infinity, agree? So let's call this, yeah, good. Shh. Let's call this point infinity 2, because it's the point at infinity of this equivalence class. Let's stop talking. Then there was the point at infinity where the other lines met. Let's put that out here. I can use whichever color I want, because the colors are the same.
I want to get beat up in college. Yeah.
Alright, and then this is infinity, let's call that infinity 1. Okay, and then of course, I have more lines, right? But the rest of my lines are just like chill, right? Where are they? There's the horizontal ones. Can someone give me that brown?
Like one of these, right here?
Just one of those browns.
I don't know if I did mark.
Cha. That is infinity 3, and thank you. Then I have the vertical lines.
Wait, that says a lot of velocity.
Yeah.
And
Yeah,
that's
it is.
Something more hard to see because just gray.
Okay, and finally we make the circle at infinity through, and there is our finite projective plane model. Now, some justification is in order, such as, how do I know that this is a finite projective plane? Check the axioms, but I don't want to like mindlessly check them all. I want to like argue algorithmically. I want to argue that my algorithm like correctly will produce always. So why will it? Well, just like notice that like what would happen if I okay. you saw the squares that made like these 9 points, right? What is the square that, hope I'm not doing this the wrong way, I think I'm not. What is the square that would generate the 3 green lines?
1, 1, 1, 2, 2, 2.
Yeah, he gets it. It's like the 1, 1, 1, 2, 2, 2, 3, 3, 3 square. That would, if I'm just connecting the 1s, connecting the 2s, and connecting the 3s, that would give me the equivalence class of my 3 horizontal green lines. And what square would give me my 3 brown vertical lines if I'm just connecting all the 1s and connecting all the 2s and connecting all the 3s? It's like this one, right?
And those are orthogonal to those.
Yes, and though these are not Latin squares, they are sort of orthogonal, so to speak, to the original 2 Latin squares. Because you could almost define a Latin square as a square which is orthogonal to these 2 squares. Because built into the very definition of the Latin square is that the 1 appears in each row in each column. And if 1 appears, I guess specifically, why are these 2 squares orthogonal? Which of the, let me try to articulate
You
this.
can't get 2 in the same number in the same row.
In the same row, exactly, right? These 2 are orthogonal. These 2 squares are orthogonal because we're going to have 1, 1, well, going from left to right. We're going to have 1, 1, 1, 2, 1, 3. And so it is the fact that each number appears only once in each row that ensures that these 2 squares will be orthogonal. And since these 2 squares will be orthogonal, what effect does that have on my finite projective? What are the implications for my finite projective plane? What property does that ensure on the finite projective plane?
Oh, you only get 1 intersection with those lines.
Yes, right? What we can guarantee is that every one of my, it was supposed to be like pink, orange, and red lines, the ones from the first equivalence class, the equivalence class of parallel meeting at infinity 1, these will be guaranteed to meet exactly once with each. Which are these again? These are the green lines. They'll be guaranteed to meet, and they'll be guaranteed to meet exactly once. It's because this is a Latin square, and because it's sort of orthogonal. Does anyone want a better explanation of that, or more explanation? Or should we just keep going? You want more?
I have a question.
Yes.
How do we pick which parallel lines intersect with which?
How do we pick which? Say that one more time.
I mean, we kind of just drew some intersections between parallel lines, but how did we know which parallel lines to intersect?
It was based on the equivalence class, right? These 3, you're talking about when I made the points at infinity?
Sure.
Is that what you're talking about? Yeah, so these, the 3, so this Latin square produced 3 lines. The line through the